Good morning, everyone. So we're going to get started with this particular problem. So if a car's engine is applying a force of 750 newtons, so that the car with a mass of 25 kilograms is accelerating at 2 meters per second squared, what is the force of friction acting on the car? And I also want you to draw a free body diagram for this scenario. So once again, if a car's engine is applying a force of 750 newtons, so that the car with a mass of 25 kilograms is accelerating at 2 meters per second squared, what is the force of friction acting on the car? And then I also want you to draw a free body diagram for this scenario.
Is this warm up on an assignment somewhere, or should we just be doing this on a separate piece of paper?
You can just do it on a piece of paper or something. It's not on any particular document or anything.
Should we consider that there is friction? Sorry, like actual friction against the car, like where it's going to?
Yeah. We're trying to figure out how much that friction is.
Yeah, because the car, like as I said, like I think last time, it does use friction loosely to move. So
Yeah. So we're considering that the friction is friction is pushing against the car
okay.
and it's slowing it down. Yeah.
Is there also a resistance in this problem?
Ignore air resistance. In general, you can ignore air resistance unless the problem specifically specifies it.
Do you want us to put the answer in the chat or?
You can just message me your answer. That's fine. Yeah, or you can just put it in the chat. That's fine. I don't have a poll or anything today. Take another minute or two to figure this out. Okay. So let's start off with drawing a free body diagram for this problem. So for starters, there's always the force of gravity acting on an object. Down. In this case, the car is not going to be accelerating up or down. So you know that there has to be a force pushing it against it, pushing it upwards. Because the car is on the ground, there's going to be a normal force from the ground pushing it up. There's going to be an applied force from the engine. And then there's going to be a friction force pushing against it. Now the friction force is going to be smaller than the applied force because there is a net force because the object is accelerating. So the friction force is going to be smaller than the applied force. Well, in order to figure out the friction force, we're going to use Newton's second law at net equals mass use acceleration. We're only going to work in the horizontal direction. We're going to ignore the vertical direction right now because we don't really need it. And so we know that the net acceleration of the car is 2 meters per second squared. We know that the mass of the car is 25. So we know that the net force has to equal 50. So what forces comprise our net force in the horizontal direction? We have our applied force and we have the friction force. So we know that the applied force minus the friction force should equal 50 newtons. The applied force was given to be 750. 750 minus the friction force is equal to 50. And so the force of friction should be 7 newtons. So that's pretty much just the gist of how to do problems like this. Set up a free body diagram, set up a net force calculation, try to identify which forces comprise the net force, and then solve for whatever you're looking for. Does anyone have any questions about this? Okay, so we're going to finish where we were on Tuesday. We're going to finish talking about friction, and then we're going to work on the free body diagram and Newton's second law assignment. I pushed back the due date to next Thursday, Friday, so we'll have today to work on it and next Tuesday. So we should have plenty of time to finish it. Okay, so where were we last time? Oh, so last time we were talking about kinetic and static friction. Just as a recap, there are two kinds of friction. There is kinetic friction and there's static friction. So kinetic friction is how much is the friction that a moving object deals with. And so usually when you think about friction, you think about, moving. So that's kinetic friction. And the static friction, as a recap, is just the friction that you have to overcome in order to move an object. The reason why objects don't move on their own is because static friction keeps them in place. And so if you want to move an object, you have to overcome that static friction. Once you apply enough force to overcome the static friction, the static friction essentially, then it switches over to kinetic friction. And the static friction becomes zero. Well, it just becomes irrelevant is a better way of thinking about it. And similarly, when the object is not moving, the kinetic friction becomes irrelevant. So how do you figure out your kinetic friction? Well, the kinetic friction is related to the normal force of the object, basically how much the ground is pushing on an object, and the coefficient of kinetic friction, which determines basically how much that surface, how much friction that particular surface has. So how much friction an object feels is equal to its coefficient of kinetic friction, called the mu k, times normal force, F subscript n. And that force of friction opposes the direction of motion. So the mu k, the coefficient of kinetic friction, will differ between surfaces. So I mean, sometimes I will ask you to determine it. Sometimes I will give it to you. I will never ask you to remember like what the coefficient of friction is for a rubber or something. I will never ask you to do that. But in the context of the problem, I may ask you to figure it out based on other information in the problem. So that is something that you will have to consider. But yeah, so what I also want to reiterate is that it can be easy to get locked into using this formula to figure out friction. So this is a direct way of figuring out your friction. Sometimes you may have to use an indirect way as the warm-up problem, right? In the warm-up problem, we didn't use this formula to figure out our friction. We sort of examined it in a different way. So this is a direct calculation. Sometimes you may have to figure out your friction in a different way as well. So that's something I also want you to consider. This is just a more direct way of figuring out your friction. So just like kinetic friction has a formula, static friction also has a formula. So once again, static friction applies when the object is not moving, and it's the friction induced by the surface to keep the object from moving. When the object is moving, the static friction is 0. So to calculate static friction, we can use pretty much an identical formula. The force of static friction is basically the coefficient of static friction, mu s, times the normal force. In this case, the notation is n. It should be F subscript n. But it's the same thing. It's the normal force, just like the coefficient of, just like the kinetic friction force. The coefficient of static friction is once again related to the surface of the object. This will pretty much always be different than the coefficient of kinetic friction for the object, for the surface. So the two will pretty much never be the same. So that's something that sometimes I may ask you to figure out what both are. So that I don't want you to assume that both are the same. I also don't want you mixing up the coefficients. I don't want you using the kinetic friction for static friction and the static friction for kinetic friction. So don't mix them up. What is different here is that the force of static friction, the static friction force, is less than or equal to the coefficient of static friction times the normal force. So why is there a less than or equal to? The reason why this less than or equal to is because this tells us the maximum static friction force the surface can induce, right? So let's say you apply a teeny weensy amount of force, right? Well, if the static friction force was always equal to this number, what this means is that the applied force is going to be less than the static friction force, which means that your object is going to be moving backwards, or accelerating backwards, which doesn't really make sense, right? If you apply very little force to an object, it just doesn't move. It doesn't start accelerating backwards. So the static friction force just tells you how much the maximum friction force that surface can induce. So, so basically, it's like if your applied force is less than the maximum static force, then the static force induced will be equal to the applied force. Once the up to the maximum of the static force, static friction force. So I just want you to think of it as basically, if you don't apply enough static force to move the object, then the static force, friction force will be equal to that, to your applied force. Once you apply enough force to overcome the maximum static force, right, then this whole thing turns to 0 pretty much. When it doesn't turn to 0, it's more like it just becomes irrelevant. It just becomes, the force doesn't apply anymore. So that's something you should consider. Okay, so mu k and mu s, these are the coefficients of kinetic and static friction for different surfaces. They just tell us how much friction a surface has. They do differ from surface to surface. For example, ice has a coefficient of static friction of 0.05, whereas asphalt has a coefficient of static friction of 0.7. So if you notice here, asphalt has like a coefficient of static friction of about like 14 times bigger than ice, which makes sense, right? It's a lot easier to move an object on ice than it is to move it on asphalt. Where do these coefficients come from? They're basically ratios between the normal force to the frictional force of an object. So what happens was engineers and scientists, they will basically measure the actual frictional force of a surface. They'll compare it to the normal force on the object, and then that ratio is how you determine the coefficient of friction. So this, yeah. So that is pretty much all that is pretty much how friction works, pretty much. What we're going to do now is we're going to do a practice problem here. Where we are given the coefficients of friction for a particular surface. So in this practice problem, we have a refrigerator with a mass of 1,000 kilograms that is at rest on asphalt. Asphalt has a coefficient of static friction of 0.9 and a coefficient of kinetic friction of 0.7. So we want to figure out the minimum force you must apply in order to move the refrigerator. Make sure you draw a free body diagram for this scenario. And then once you've applied just over the minimum force, so this should actually say sort of just over the minimum force, the refrigerator is now moving. What is the acceleration of the refrigerator? For the second one, I just want you to assume that you are applying the minimum force so that you're just applying the minimum force needed to make it move. Yeah. Let's take another 2 or 3 minutes. So force is measured in newtons. So if you want to label the units for force, you use newtons, which is just a capital N. Newtons, Newton, like a fig Newton. Big Newton. Big Newton. So to start off, I'm going to draw a free body diagram for when the refrigerator is not moving. So when the refrigerator is not moving, so the static friction force is less than or equal to that number. Yeah, the static friction force is less than or equal. So, okay, so our free body diagram here, we have our force of gravity going down, the normal force going up. We have our static friction force, or we have applied force, and then we have. So the case we want our applied force to be less than or equal to our. So we basically just need to apply enough force to overcome our static friction force. So which means that my applied force should be greater than or equal to. So we're going to use the formula for the static friction force here. We're going to use mu s times the normal force. So we want our applied force should be greater than or equal to this number. Well, it really should be greater than. So this is just a number. It's 0.9. So we need to figure out the normal force. So how do we figure out the normal force? Well, in this case, the net force in the y direction is 0. So which means that the normal force minus the force of gravity should be 0. So our normal force should equal to the force of gravity. So our normal force should equal mg. So that means our applied force should be greater than or equal to 0.9 times our mass, which is 1,000, and conservation of gravity, which is -8. So our applied force should be greater than or equal to 8,820. So for the moving case, it's the same free body diagram, except that our applied force is going to be bigger than our kinetic friction force. So our kinetic friction force is going to be smaller than our static friction force. So in this case, we're applying a force of 8,820. That is not our net force. We don't actually know what our net force is, so we need to figure that out. So the net force in my x direction is equal to my mass times my acceleration in x direction. And this is what we want to find. So the net force in my x direction is my applied force minus the force of friction. This is equal to my mass times my acceleration in x direction. In this case, we're working with kinetic friction. So my applied force minus my kinetic friction, which is mu k to the normal force and mass acceleration. My applied force is breathing from this problem, so 8,820 minus 0.7 times 1,000 is equal to 1,000 times my source in the next direction. It is what they have. Does anyone have any questions about what I did here? Okay, so what I want you to do before you start the assignment, I want you to just spend a few minutes just trying to revisit your meter stick explanation from Tuesday. And then we tried to explain what happened in the meter stick. So I just want you to use what you've learned about friction and try to see if you can revisit your explanation, try to make it a little bit better, a little bit more accurate. The slides are on Canvas, so you can go back and review them if you need to. So go to your graphic organizer, just try to improve your explanation for the meter stick a little bit. And then when you're done with that, you can just submit it on Canvas. I'm not grading it, so you don't need to worry about your explanation being perfect or or even particularly accurate. Just do your best here. So don't spend too much time on that. And then once you do that, you can start working on the main assignment.
Mr. Hu, would you mind going back to showing the board? I didn't get to see all of it. I just need to take a picture very quickly. Thank you.
Which assignment should we start doing? Also, you're showing us your OBS, sir.
Showing your OBS. Okay, whoops. Hold on.
You're not even using Streamlabs? Shake my head.
Streamlabs. OBS is the way to go.
I'm just kidding. I'm also using OBS. But seriously, should we do the F is equal to MA and FBD is introduction assignment?
Yep.
All right.
Yep. Yeah, but OBS is the way to go. Okay, let me clarify a couple of things. Okay, so first off, on question 4C, I realized that I wrote two coefficients that were both static. I changed it, so 0.05 should be your static friction coefficient, and 0.03 should be your kinetic coefficient. So make sure, so if you just check the document, it should be updated. Another thing that I sort of forgot to so I initially when I initially wrote the assignment, there was a lot of explain your answers. I don't want you to explain. I don't care. No offense. I don't care. So just do the problem. You don't need to explain it. Just do the problem and that's it. So yeah, don't explain it. That should be. Other than that, let me know if there's anything else, other problems or complaints you have, and I will resolve those. Yeah. Okay, 9:50. It's 9:55. It's 9:55, so we're out of time here. So, homework. Well, I mean, you can try to keep working on the assignment, but we'll keep working on it next week. So if you have any questions, you can always ask me next week or come during office hours. Other than that, that's it for today. I will see you all next Tuesday, and have a good weekend.
Thank you.
Thank
See
you.
you,
Have a nice
Mr. Hu.
weekend.
Thank you.
Farewell.
Thank you.
All right, see you.